Thank you very much for inviting me to come speak today. So I'm one of the, the evangelists for computing at the laboratory and in some respects within the DOE system. And I spent a fair amount of time over the last few years working on various very large computing projects at Argonne, starting out with the TerraGrid project, the lab's own supercomputer center, and then for the last 2 years, I've been helping establish this new kind of computing center at Argonne, a leadership computing facility that I'll tell you about today. And that just started yesterday, was the official DOE dedication of that facility. And so some of the things you'll hear may be fairly new to you, which I hope you'll find interesting. And then I'm now looking ahead at the future generations of computers, and if I have a little time at the end, I'll tell you what we're doing along that front as well, and working specifically also on fostering the increased use of high-end computing in science at the laboratory across the whole lab. And so that's been a really fun pursuit because I get to work with a lot of people in a lot of different disciplines. I don't know how much you guys know about Argonne National Laboratory. Here's just like the world's quickest tour of the laboratory on 2 slides. Argonne is the nation's first national laboratory. Like many of the other national labs, it spun out of the Manhattan Project, but Argonne's early years had a lot of dedication to the design and engineering of nuclear power systems for electric power generation and other kinds of power production. Okay, every nuclear power plant I think in the world today has technology that was developed at Argonne. But a lot has happened between the 40s and 50s and 60s and today. The mission of the laboratory has gotten a lot broader. It's now a Department of Energy Office of Science laboratory. Okay, and there are about 2,900 employees there now. A little less than half of those are PhDs. And every year we have about 5,000 users of our scientific user facilities. One of the cool things about working in a national lab is we end up being the custodian of some of the most unique and largest and most important scientific resources for the community that there are in the nation. Okay, it gives us about a $500 million budget. And the other cool thing about the lab is that we're sitting on a wooded site, which is situated itself in the middle of a forest preserve. Okay, and so nature is always just outside the window. We have quite a lot of sponsors. Most of the work, about 80% of the work is funded by the Department of Energy, various parts of it, mainly the Office of Science. Okay, it's mainly open science research laboratory, okay, serving, advancing the frontiers of knowledge. I mentioned just a moment ago that we operate a number of user facilities for the whole nation, and really many of them have international usage. The Advanced Photon Source, the brightest source of light in the country for this kind of experimentations at Argonne. Undoubtedly the centerpiece. The Center for Nanoscale Materials, which just opened within the last year. Okay, and then the probably one of the most important sources of isotope accelerators, the Argonne Tandem Linac Accelerator System, is also at Argonne. And then finally, the thing I'm going to talk to you most about today, the Argonne Leadership Computing Facility, which began in 2006, but which just got its production machines operational within the last couple of months or so. And so the great scientific strength of all the staff there is complemented by an array of these national user facilities and other experimental and computational facilities on the site. In addition, we have quite a wide variety of academic programs, collaborations with universities and industry, programs for undergraduates, postdocs, visiting faculty at the lab too. If you're interested in some of those things, contact me and I can hook you up with various kinds of programs, internships, for example, as well. So let's talk about computing a little bit. So the projects I've been involved with most recently are sponsored by the Department of Energy's Office of Science, okay, one of the largest scientific enterprises sponsored by the federal government, especially in the physical sciences. And in particular, part of that office is the Office of Advanced Scientific Computing Research. They have the mission to not only do research in computer science, math, advanced algorithms and tools and ways of making very large applications to solve large and complex problems, but they're also the custodian of the Department of Energy's research network and the big national supercomputer facilities for the department. And there were two kinds of supercomputer facilities. Originally, there was only one. So starting back in, depends on how far back you want to go in your definitions, but say in the 70s, and certainly by the 80s, they've had a center out in California, the National Energy Research Supercomputing Center, okay? And its missions to deliver high-end capacity computing, okay, cycles to a lot of projects, okay? It's devoted largely to DOE-funded projects. About 80% of the time goes to that. 10% of the time goes to a smaller number of projects that occasionally need really high capacity, okay? Those allocations are typically annual. But what was happening was people are using computing more and more in their research, and there really just wasn't enough time on a machine like that and a facility like that to handle the really big complex problems that people wanted to be able to run. And so the notion was, let's create a new kind of facility, a leadership computing facility which is dedicated to a small number of very large and very complex projects that simply couldn't be done on any smaller kind of resource. It really need some of the most powerful computers in the world in order to do their work. And so in 2004, the DOE issued a solicitation for a leadership computing facility. And what happened was that Argonne, Oak Ridge National Lab, and Pacific Northwest National Lab teamed up and put in a joint proposal, and we won this competition. Okay? And we proposed that that the Department of Energy deploy two kinds of computers. So we basically answered one proposal with like a proposal for two sites, okay, where we would deploy the Cray X series machines, okay, you remember the X1, X2, now the XT series machines, okay, down at Oak Ridge National Lab. And then we'd evaluate and deploy IBM's brand new BlueJean series at Argonne, and I'll tell you a little bit more about that in a moment. And so that's what we did, okay. The Oak Ridge Center started first because the Cray X series were available at the time that the proposal was first funded. But if you remember, back in 2004, there weren't any BlueJeans yet. We knew some things were coming. And so Argonne obtained one of the first BlueJean systems, the BlueJean L, about 6 teraflop system, for evaluation. Okay? We built a large community around it. People all over the country and really around the world got to kick the tires. And a large number of applications got ported in that process. And it was so successful that by 2006, DOE was coming to us saying, well, could we use some of this time for production? We know this is only like an evaluation and research machine, but you know, people have these computations that they need to run. We need the capability. Could you take on some InSight projects for us? And so we began in 2006 with 6 InSight projects, 9 in 2007, and we'll have 20 here in 2008 now. And so in 2006 and 2007, we began to plan the real deployment, the production systems that we've been installing. And due to the timing of the funding and the time it takes to plan a major center, and these machines are big and complicated. There are a lot of details. The projects are a relatively formal project in terms of how DOE assesses whether you're ready to spend make the major acquisitions in a program like this. Okay, so we went on and decided we would get the next model of BlueJean, the BlueJean P. Okay, so what we just took delivery of, starting in October and ending in December, okay, was a 556 teraflops BlueJean P computer. Okay, it has 40,000 nodes, over 160,000 cores or processors in it. That's about the power of maybe 70,000 good laptops, okay, nowadays. It has 80 terabytes of memory. Every node has 2 gigabytes of memory. If you rack it up, it's about 80 terabytes. That would be about 150,000 CDs worth. And there are 8 petabytes of disk storage. Actually, it's closer to 9 petabytes, okay, if you include all the storage that we bought for the system. It's just shy of 10,000 disk spindles, okay, in this machine room, okay. And you can imagine that architecting, checking out, and making sure everything works at high speed for a disk system that big is no simple matter, and also was a computer system this big. You can transfer data from the BlueJean to this disk system at over 100 gigabytes a second sustained. That was one of the design points in the system. And you might think that you're really going to need that because you're going to be doing calculations, okay, on a 500 teraflop machine. People are going to be using this machine every day whose data sets are in the 100 gigabyte, couple of terabyte, maybe even larger, just for one run. Okay, so we got to think of what we're going to do with all that data. We can't leave it all on disk, even though there's 8 petabytes, and that sounds like a whole lot of disk space. Okay, it's going to fill up pretty soon. Any center will tell you that that's what happens very quickly. And so we also put in the first phase of a tape archive system, or robotically accessed LTO4 tape cartridge system. The first phase of it, the first unit, holds 10,000 tapes, each of them about 800 gigabytes, so it's about 8 petabytes. And as the technology improves, and we'll also continue to add libraries, we expect in about 4 years to have about 100 petabytes of tape storage capability in the system as well. It's been a very interesting project because this is literally one of the very first BlueJeans. It wasn't quite the first one to leave the factory, but in fact we had the earliest access to the machines before they were even shipped. So we got the opportunity very early to work with IBM, giving us the opportunity to test our codes out and port tools early, and to find a lot of the early bugs, most of which I'm pleased to tell you have been solved by now. And so it's been a very interesting process. So let me tell you a little bit about what it takes to build a machine this big. So as you know, most of your PCs have 1 or 2 CPUs. Okay, you solve a computational problem by translating that problem, that algorithm, into a stream of instructions and feeding it to a processing unit, right? And so a typical PC nowadays is about 2 to 10 gigaflops, 2 to 10 billion arithmetic operations or floating point operations per second. If you want to make a parallel machine so that you can harness the work of more than one CPU and the memory, perhaps of more than one, that's directly accessible of more than one processor, then you've got to lash these things together. You've also got the problem of breaking up your algorithm or your solution into pieces that can be concurrently executed, okay, on a number of processes at a time. In principle, that's not too difficult on a lot of scientific algorithms, except that there's often quite a number of dependencies, okay, where information that one processor has to be shared with another one, or a processor needs an update of the latest physical conditions nearby, okay, or the latest part of the solution being done by another part of the machine. And so the processors have to talk to each other. And so by necessity, then, you need some kind of communication fabric, okay, connecting these processors together. And obviously, if the fabric was infinitely fast, then you wouldn't have to worry about its speed, but in fact, we're dealing with the kind of technologies that we have today. And so there are limitations in this connectivity, okay, that determine, in some respects, the balance of the machine. And there are topology issues too, right, about how you wire these processors up that determine things like the network diameter, okay, and the detailed performance characteristics of it in nearest neighbor operations or in collective operations. A collective operation is one where some processor or some group of processors has to tell everybody else in their group or get data from everybody else in their group in order to complete a task. Okay, so all of those things are design trade-offs when you build a really big machine like this. And as you might imagine, there's overheads too in doing that communication and coordinating that work amongst all of those processors. And hopefully that coordination work and that overhead in doing the communications won't kill you before you run out of processors. Okay, and you'll be able to scale. You'll be able to use more and more processors and do a very, very large problem on a very big machine, or do a modest-sized problem very fast on a very big machine. Okay, so what's it look like when there's 4 processors? What's it look like when there are thousands, tens of thousands, or hundreds of thousands of processors? Okay, so this is the chip. This is a little picture of the chip in the BlueJean machine. It's a quad-core chip. It runs 850 megahertz. That's quite a lot slower than the processor that's probably in your laptop, or that has been in your laptop for quite a long time. But the reason for that is power consumption. I'll talk a little bit more about that on the next slide. It has a modest amount. I don't think you can actually read that number. It's 8 megabytes of EDRAM on the chip. Okay. In addition, all of the communications routing is on the chip. all the information to drive 5 different kinds of networks, a 3D torus, okay, tree network, a barrier network, okay, control network, okay, and an I/O network, are on this one chip. Okay, so that when you build a computer out of that chip, all you do is add DRAM memory chips, in this case 2 gigabytes for the chip, and you make a card which is literally a complete computer, including I/O and Ethernet interface, okay, and communications interfaces to the other processors. And this here that I have in my hand is one of those cards. That's all the bigger it is. Okay, one node, 13 gigaflops. And it's got a heat sink sitting on top of it, okay, but it's not particularly hot, okay, but it will be because we're going to jam a whole lot of these in our packaging plan in one box. We're going to put 32 of these cards in a chassis, which IBM calls a node card, okay, so that's going to have about 64 gigabytes of memory. Then we're going to take 32 of these chassis and we're going to put them in a refrigerator-sized box, a rack, okay, and if you did all the multiplication right, you'll know that there are now 1,024 nodes, 4,096 processors in that box, okay? And there's 2 terabytes of memory in there, and that box will do almost 14 teraflops a second. Size of a refrigerator. Very small. And then to make a really big machine, we hook the networking up between the boxes. The main cables hook up the torus network. That's where most of the data lines are, between boxes. We hook them up in a regular pattern between the rows and down the row of a machine. Typically, people build rows that are about 8 boxes long, and then the number of rows that you need, although you can vary that to get different X, Y, and Z dimensions in this 3D torus, right? If you had 72 of those racks, you'd have a machine that had a peak performance of a petaflop. And in fact, the design size of the machine would permit you to do 256 racks and get a 3.5 petaflop machine. A little bit cut off on the edge here, so hopefully that won't hurt me won't hurt me too much later on. If it does, I'll switch a resolution. So how do you talk to this machine? So you're a software developer or you want to run a program. So you talk to a front-end machine. It's a standard IBM Blade server in the case of our machine. And it runs a lot of software that you'd be familiar with, okay? So it runs the IBM XL compilers, XLC, XLF, runs the IBM General Parallel File System, and it runs, uses the IBM Scientific Subroutine Libraries, MPI, and stuff. So it'd be a very familiar environment if you've been used to using, say, IBM clusters or other clusters for your work beforehand. Another interesting thing about this project, though, is that it came out of a joint research and development project, which is a little bit unusual, sort of a design-build approach, where the Department of Energy, with point laboratories at Argonne National Lab and Lawrence Livermore National Lab in California, okay, had an R&D contract to actually develop the design for this computer, okay, along with IBM engineers who did most of the hardware work at their T.J. Watson Research Laboratory, and the manufacturing folks and some of the software work came out of IBM's Rochester facility up in Rochester, Minnesota. Okay, so what the DOE contributed here was really our science-driven requirements. And so imagine a machine that's designed from the beginning, okay, with the understanding, with the in mind what kind of applications are going to actually run on it. In fact, using some of the applications from the DOE user community, okay, in the evaluation of various design elements of the machine right from the beginning. And also, we have a tremendous amount of experience, decades worth, in fact, operating very large supercomputer facilities, okay, among the DOE labs. Some of the first Cray computers were deployed in the weapons labs and other labs in the DOE system. And so we contributed that, and IBM contributed their very advanced architecture and world-class engineering group for both the chips and the packaging, manufacturing. And remember here, we've got a machine, okay, that has something like 500,000 chips in it. Okay, so you've got 40,000 nodes. Each one's got 21 chips. Okay, 800,000 chips in it. Okay, reliability is really important. That's why all the stuff is soldered on this board, for example. Okay, the DIMM memory connector is one of the big failure points on the machine you have at home and in your office. Okay, so they took into consideration all of that stuff, and actually engineered in the mean time to failure right from the design point in the machine. It's quite an interesting process to go on with. And another thing that I thought I would take a moment to tell you about while I'm speaking about it here is that, because I think this machine is ahead by a generation or two from a lot of other stuff that you see in the world today, and that is that in how it uses power. We've begun to hear that power consumption in data centers is starting to become a big thing, okay? Because if you run the math in a typical enterprise data center now, over the lifetime of their equipment, half of their cost is in electricity, or upwards of half of their cost. Okay. In addition, the other thing that you probably know is that what's going to limit the kind of chips we build and the kind of machines we build using silicon technology is the amount of power that's absorbed on the chip. There's a lot of work being going. I enjoyed hearing about at the poster session today of people working on lower power solutions, okay, design approaches for integrated circuits, because it's very, very important stuff. And the IBM guys know this in spades. I mean, it's the way they think there. And so BlueJean, the whole line, was designed from the start to be much lower power. That's why it has a lower clock frequency, for example. But they did a bunch of things on here. So you start out with a lower power core, okay, on the system. This is a little picture of the chip. Okay, you can see some of the memory laid out in blue on here, and this is the processor up there, okay, and there are 4 of them laid out on there. So the design of the chip, okay, in itself has many features in it that reduce the power. And one example that some of you IC guys may be familiar with is no large SRAM, okay, on this chip, because they're very power hungry. They use this EDRAM instead, okay, which is not quite as fast. But remember, this chip is running at a lower clock speed, so you don't need all that speed. It drives you to have the big SRAM for the shared memory on the chip, okay? In addition, the router's on chip, so you don't have to drive signals off, okay? You drive the DRAMs directly, okay? There's no resistors. There's no other memory controller between the chip and the DRAMs. That saves you a lot of power. A great deal of the power in modern computers is actually going to driving the memory. Okay, and a number of other things like that, okay? And the other thing is, we were talking about processor voltages or chip voltages with one of the poster presenters today. I see I'm really running off there to the side, huh? So when you manufacture integrated circuits, okay, what comes out of the assembly line has some processing variations in it, okay, process variations amongst the chips. So some chips will run a little faster than others. Some chips will run at the rated speed at a little lower voltage than others. And so IBM creates sets that operate at a single voltage and then runs the whole card, the whole node card at that voltage too. So there are 3 different voltage node cards on the machine. That alone saves 20% of the power on the BlueJean system, okay? A rack of BlueJean, the peak power is about 37 kilowatts per rack. And this is what 40 of them look like in our machine room. With the storage, it takes only 2.2 megawatts. It's less than 4,000 square foot with all the disk storage that I told you about. Okay, it takes about 600 tons of cooling capability. Okay, if you look at the Green 500 list, which lists the top 100 systems, and look at the non-BlueJean systems, they all take 2 to 5 times as much power for the compute part as this does. So that's pretty important. So how do people get to use this machine? I mentioned early on that most of it is dedicated to a small number of large projects. And so the leadership facilities have 20 to 30 large projects. It's a peer-reviewed process. It's completely open. Okay, whether you're funded by DOE or some other agency or some private grant, okay, whether you're at a federal lab, university, or an industry doing open research, okay, with very few restrictions. Okay. If it's open research, it falls in that category. It would be fine. Okay, you can apply to this program. There's an annual call. The next call for proposals will be probably in May. They'll be due in August. And the proposals will be awarded for start in January. So if you're interested, drop me a line later or contact me afterwards, and I'll explain how to get into the process. I should have put the URL on the slide. It's very simple, hbc.science.doe.gov. That's where you go. It's peer-reviewed. Okay. The grants are up to 3 years in time, in computer time. So you think big. Okay. Think of those problems that you dreamed of doing, but you never could get enough computer time to do. Okay. For example, a typical project in 2009 is probably going to use between 25 and 100 million CPU hours a year. Okay? Because you're looking at machines like this 500 teraflop BlueJean that is capable of doing a billion CPU hours a year on all those processors, okay, in aggregate. So big problems. And your problem should be able to run on a quarter of the system. Okay. So let me give you a few examples. Let me talk a little bit about, I thought I'd talk about some of the science that's being done on this machine to sort of give you an idea of what kind of problems need a machine that's this big or bigger. And I thought I'd talk about supernova to begin with, because it's a project that I've been associated with recently. It's a collaboration between folks at Argonne National Laboratory who are doing performance engineering work on the code, and the ASC Flash Center. It's a Department of Energy and National Nuclear Security Administration funded project. It's been going on for the last 10 years at the University of Chicago. You may know that we have a joint computation institute with the university in Argonne. And this is a project that's been going on quite a long time. It's about 10 years old. At one time or another, there are 15 to 20 people working on the project. It's a pretty substantial sized set of code. So I explained a little bit about supernova and why you would care about them. Type 1a supernova pretty much seem to have, okay, the same brightness, okay, when they explode. And that's very cool, because if you know something happens out there in the universe that has the same brightness, you can gauge how far away it is and how fast it's moving away from you by the redshift. And so combined with other observations, astronomers have used the type 1a supernova. That and other observations led to the discovery of dark energy that's accelerating the expansion of the universe, and that's a very recent development. Supernova also play important roles in chemical production. They fuse carbon and oxygen atoms into heavier atoms, okay, like magnesium, silicon, sulfur, iron, and nickel. Okay. So the question is, how do they explode? And this is a really pretty interesting problem. Okay. What's thought, I mean, we haven't watched one all the way through the process, obviously, is you start with a small compact star that's a binary that has another star nearby. And over time, so this small compact star is maybe about the size of the Earth. And over time, it accretes matter from its neighboring star until it reaches about 1.4 times the mass of our sun. And then it explodes. Okay? Now, stars burn in two ways. Okay? The general burning process, which our sun does, which is called deflagration. Okay? And then there's the explosive process, which we know is part of the supernova process, called detonation. But the thing is that if you look at the observations, you can tell that it's not all one or the other. So the question is, what is the process? And what can we learn about that? Because if you look at the brightness of these supernovae, there's about a 15% variation in the type 1As. And if we actually understood the mechanisms behind it, and we could get our uncertainty as what was happening out there down to 1%, it would make a lot better standard candle. We ask the observations to tell us a lot more about what's happening in the universe. And so that's part of the aims of these computations here. Okay, so the nuclear energy, nuclear reactions, power the explosion, okay, and the light you see from a supernova is really the radioactive decay of these product elements, in particular 56 nickel, okay, degrading into other elements like cobalt, okay, emits the light that you see that makes the bright light of the supernova in general, okay. And so, until recently, no one had a model, okay, that would actually explode. Okay, so you imagine lighting a star in some way, okay, and then following the model, okay, and actually seeing it blow up, okay. And so this is one of the first models. This comes from the University of Chicago work. This is not done on our BlueJean, okay. So this thing, the explosion begins with an ignition, a deflagration ignition, okay, slightly off-center in the center of the star. You can see a little bitty dot in the middle of the star, right in there. This bubble's going to scream up, okay, it's going to rise, okay, in the star. It gets to the surface, and then these pressure waves, like a tsunami of hot star matter, the red stuff is the hot stuff, you see waves of it, go around the star to the back side, and you see they're going to coalesce on the other side. This visualization will change scale several times. When they hit the other side, there's so much mass, okay, and so much energy in that, that's what's going to detonate the star. Okay, that wave travels back and will change scale again, and boom. This isn't quite the resolution that we'd like to have, but it's a very interesting simulation, and it's right. Okay, so this is the gravitationally combined detonation model. And an important thing I need to tell you is why doesn't that stuff just keep going out when the bubble hits the top? Gravity is strong enough to keep it flowing along the surface of the star, okay, and not just spewing out into space immediately. So this is characteristic of a mesh kind of model, okay, where we've divided up space into boxes. And you'll notice, and here's a sample of the mesh for this problem, as you can see. So remember, this is a pretty big object, and yet the things that are happening are starting out and happening at fairly small scale. Okay? So I'm showing you the mesh, and the stellar surface is in blue. I'm going to watch how the mesh evolves. So one of the more efficient way to do computations of this type is called adaptive mesh refinement, okay, where we're going to allow the size of the boxes to change. It's driven, in this case, by some of the gradients in the problem. It determines how the mesh is remapped at intervals. Okay, you can also use particle tracking to do there's a very general mesh remapping capability in this code. Okay, so let's watch, I forgot to hit it, there we go. Let's watch how the mesh evolves here. You can sort of barely see it because there's so many mesh boxes in this. But you can see the burning rise to the surface. You can see the mesh size change as it spreads around. Okay, so that's typical of a modern adaptive mesh refinement problem. The mesh is refined periodically, and this is also the basis by which you can immediately imagine dividing this work up amongst a very large parallel machine. Then you might say, yeah, but those boxes probably don't have the same amount of work in each box, and that's true. And so load balancing, deciding how many boxes go to each processor, and balancing the number of boxes that a processor handles, as well as the change in the mesh as time goes on, is some of the complexity of writing a very efficient large code for a big machine like this. So to get the idea of how big these calculations are and how complicated they are, okay, so three things commonly drive people to petascale and beyond, okay? And this problem has all three, okay? It has a large range of scales, okay? Following the nuclear burning requires 1 to 10 kilometer resolution, whereas the radius of the star is 10 to the 9th kilometers. It's a large range of scales. Things are happening at really small scale, but the parts of the system are very large scale, so that drives you to really big machines. Complex physics, okay? Lots of different parts to the model, okay, things that are expensive to compute, maybe multiple models that have to be lashed together. And the need to integrate for a long time, you have to take many time steps. You've go, well, that doesn't necessarily drive you to a big machine, but it does, because what you want to do then is have the biggest machine that you can do that problem on efficiently, because you know you have to integrate it for a long time, and so you want to make the result, get the result back as quickly as possible. So it needs the widest machine that your problem can do. So the calculation that I showed you before, the explosion took those kind of calculations take about 100 to 300,000 CPU hours. They produce a couple hundred megabytes an hour. And for that study, they used about 7 million hours of computer time in 2007. That project expects to use about 80 million hours this year. And they expect to generate 3 to 5 petabytes of data. That's getting pretty large. So that's sort of the scale of some of the bigger problems. Turns out that we have a long-term relationship with the people that have been working on this code. This is the Flash code. It's got about 300,000 lines. It's developed over 10 years. It runs on a wide variety of parallel machines. Okay, it's designed for compressible reactive flows. It solves a large number of problems, as you can see the little vignettes, okay, on the slide. It handles nuclear burning, gravity, magnetohydrodynamics, tracks active and passive particles, okay. The hydrodynamics basically solves Euler's equations, shown here, okay. But the nuclear burning, adds another degree of complexity to a code like this. And then folding in the large magnetic fields that are involved in stellar explosions, et cetera, makes it even more complicated. So we used this to test out the BlueJean machines when we got it. It was actually part of our acceptance tests. And this is also one of the early science problems we've been running. So these guys got early access to the machine. And it really helped us shake down the system. Found issues, we got them addressed, okay, because it's a very efficient code. And it also does heavy I/O, so we could also use it as an I/O test. So part of the project that I'm working on, or helping with, although not running the calculations, is that one of the questions here is that what is the scale at which the buoyancy-driven nuclear burning occurs at? Okay, if it's a moderately large scale, then you can do the simulations in one way. If it has to happen in a very small scale, then you have to use subgrid models that make the simulations a lot more complicated. But no one had been able to do a calculation at a fine enough grid in order to be able to prove whether it was really one way or the other, and that's what we're doing. There's a set of tests that we're running, there's an evaluation that we're running with some of the early time on the machine to just address this single question. Okay, at what scale does turbulent nuclear burning actually occur in these models? And very quickly, this is a result of, and so we're doing calculations at several different resolutions. Taking a box, okay, and we're going to light it, okay, at the bottom. There's a box on the far right here. It's a 256 by 256 by 1024 box in this case. And then we're going to do a 512 by 512 and a 1024 by 1024 by 1024 calculation and see if we can converge that property. And we're most of the way done with the 512s. You'll see the 256 calculation here today because that's the one that I've got the result on. This is a flame front. These are the velocities, okay, that are going on in the burning. Okay, so this indicates a lot of turbulence. And this is the entropy, okay, also as a measure of the turbulence that's going on in this flame. And in the far right, it's got cut off. Okay, the flame is rising in the box. The visualization is tracking the flame front as it goes up this long and skinny box here. We're looking for convergence of this simulation with respect to the resolution and other properties of it. And you also can see here that visualization is just absolutely critical to understanding the kind of stuff that comes out of these very large computations. So let me move on and give you a couple of more examples. I have a couple more examples of things that people are doing that involve meshes. Okay. I mentioned before that Argonne was involved early on in engineering nuclear reactors for power generation. We still are. Some of the next generation reactors have some really pretty desirable properties. Some of them produce hydrogen, okay, as they're hot enough that they can There's a set of chemical processes we can use to produce hydrogen. Some are very efficient, can recycle fuel, have a lot less waste to go to repositories. This is an advanced reactor design that is liquid sodium cooled, and what you're seeing is an isosurface of velocity. As the flow continues, it gets more and more turbulent. This is a fuel pin, single clad pin, okay, with uranium inside, with a wire wrapped around the outside in order to mix the coolant more efficiently. Because even coolant, even temperature within the reactor, okay, optimizes the operating conditions of the reactor. With a machine like the BlueJean L, the 6 teraflop machine, we could do 1 pin, or maybe 6 or 7 if we took long enough. With the BlueJean P, they're already working on 19-pin simulations, and they're able for the first time ever to do the full 200-plus pin, which is the actual fuel bundle that goes in a real reactor, the design bundle that goes in a real reactor. For the first time, they'll be able to model the fluid flow in a real fuel assembly, okay, with high fidelity, and check out some of the other models that people use. And then one more example in a mesh-based calculation. Another one of the InSight projects at Argonne is Pratt Whitney, okay? This program, as I mentioned, is open to industry as well. Pratt Whitney's Connecticut engineering branch. These are the guys that engineer the next generation of jet engines. So why should you care about that? Because if these engines are more efficient, then your airline tickets will be not so expensive, right? And so in fact, they have a very, very nice design that just came out for a new gear-driven turbine that's significantly more efficient than some of its predecessors. And they're doing some basic research at Argonne, okay? And they're particularly looking at what happens in the jet engine combustors. There's another combustion problem, another fluid dynamics problem. And the really big BlueJean, okay, lets them have, okay, enough of the combustor, okay, in the model that they can actually see some of the asymmetry of more of the asymmetry of what's happening inside the jet engine. Okay, so with a smaller machine, you're assuming you're taking a little pie slice, okay, of that combustor, okay, and doing a simulation on that. A bigger machine, you can take a much bigger slice, okay, and get a more realistic view of what's really happening in there. And so this kind of a thing is pretty important for them, understanding how they're going to design next generation of jet engines. And they'll be very interesting people to work with. I'll tell you about one other class of problems and many other things that are going on. Let's talk a little bit about molecular simulations, calculations that are done atomistically at the Leadership Computing Facility. This picture here, okay, so this thing in the middle is a voltage-gated ion channel. It's a voltage-gated potassium channel. These white things off to the side are a little hard to see. Okay, these are the lipids of the membrane. So it's sitting in a cell membrane. Okay, and around here are waters and other things above and below. Okay, this is some active research that Benoit Roux's group at Argonne and the University of Chicago are doing. Okay, this is a big computation. So this is an atomistic molecular mechanics force field calculation. And basically, you could divide these atomistic calculations into two big lumps. So there's a lot of mixtures that are done as well. You have calculations that people do with these large machines which are based on first principles methods, solutions to the Schrodinger equation. Okay, where in principle you've got all the physics in there and no empirical information at all. Okay, people use those methods to determine things like the electronic wave function and all the properties you can derive from that. Of course, anybody who does these in this room knows that you make approximations both to the formulas and to the physics, okay, when you actually develop algorithms to execute these methods. And so all those things are approximations, okay? And then people also take that kind of information and model kinetic pathways with things like transition state theory, and then derive statistical properties with combinations, okay, of molecular dynamics methods and these first principles methods, things like Carpernello molecular dynamics, okay? So you can typically handle dozens to hundreds of atoms on a big machine, okay, with these kind of very exact methods. Then there's also molecular mechanics methods, okay, that use classical equations of motion, okay, and often the forces between the atoms, along bonds, around angles, okay, between molecules or parts of molecules, are empirical functions of distances and angles, right? And you integrate the classical equations, and you get things like equilibrium structures, diffusion processes, phase diagrams. Those calculations now are running up in the millions of atoms, okay, on machines like this. And let me just give you a few examples and wrap up. Okay, Giulia Galli's group uses a code called QBox, a Carr-Parnello molecular dynamics code. It's looking at water in confined states and finding some very interesting properties, okay? Unlike what was thought before, there isn't. So inside a nanotube, you have water. So how is the water inside a nanotube different than it would be in just a box of water, okay? People thought for a long time that it would be sort of ice-like next to the surface, but it's not, okay? The perturbations induced are pretty local, okay? And lateral diffusion is enhanced at the surface. So those are all pretty neat observations that came right out of the theoretical computations here. Another interesting study is we have another project from Procter Gamble. Okay, these are most people think Procter Gamble is a household products marketing company, but if you ask their CEO, John Pepper, he'll say, we're first and foremost an R&D company. Okay? They're using more and more product and process design through simulation, okay, in developing the new products. This is an example of the first ever detailed simulations of the dissolving of soap and forming of suds at the atomic level. So they're doing actually atomic level molecular dynamics calculations. These ones here were two surfactants, two common surfactants plus water. They're using primarily the NAMD code out of Klaus Schulzen's group at the University of Illinois. And then using the statistics that come out of that to compare with the experiment, and also the properties to develop their mesoscale simulations where they can do bigger systems. Okay. And so this is a company you wouldn't expect to do research this fundamental, okay, sees extraordinary value in doing these kind of things. The big machine, and of course, how could I talk about BlueJean if I didn't mention any protein folding? Okay, and so one of the other Insight projects is David Baker's group that uses a well-known Rosetta code. And some of the remarkable things that come out of the work that they've done at our center recently is that they're getting very, very accurate structures, so accurate that they can actually compare to the phase computations in the X-ray diffraction experiments, okay? And they're starting to do that feedback where they could use these calculations to help refine the structures. And no one's ever been close enough before. That means that these guys are like 1 angstrom structures. Okay? And it's due, I could go through the method, but it's due to some innovations they have in the de novo protein folding algorithm that they're using now. And I think that's pretty cool. And so they're moving on from reference models to de novo protein design and protein interface design with this work. So overall, the center is used for quite an array of different kinds of science. This is a pie chart that takes the amount of time that has been allocated to different scientific areas for 2008. Okay, 111 million CPU hours, because we started the machine in the beginning of the year, and the full machine won't be available till the summer or fall. And you can see quite a wide array. I didn't get a chance to talk about the lattice gauge theory work, okay, or some of the other materials work, which is pretty interesting too. The BlueJean is a very good QCD machine, nuclear structure machine as well. One of the things that we did, if you want to get involved, starting in 2004, before BlueJean even came out, we partnered with IBM and we formed something called the BlueJean Consortium. It's an open consortium of anybody interested in BlueJean. It helped to build an ecosystem around a new machine which had sort of a different architecture and get a lot of people interested in it and give them information about it, let them kick the tires on the machine. IIT is a member of the consortium. The institutions join, and then individual people anybody at IIT, okay, can say, add me to the mailing list or tell me about events that are coming up. We have things like tutorials and workshops periodically, provides access to a 14 teraflop BlueJean system that we have for open software development and consortium use at Argonne, www.bgconsortium.org, okay, if you want to find out how to sign up or get an account. Okay. In addition, the consortium periodically, 3 or 4 times a year, runs what we call BlueJean Watson Days, where people apply to get time to do scaling studies on the 114 teraflop system at IBM's Watson Labs. And we'll probably have something like that with the big systems at Argonne as well. So that's a completely open consortium. There's over 75 member institutions now and about 250 people from around the world who have taken advantage of the access. And then just to wrap up, I promised to tell you a little bit about what I'm doing in the future, okay? If you remember back far enough, you might argue that the sort of push for petaflops started out with a series of workshops and some support and community interest building. It began around 1995. This is probably one of the hallmark reports by Tom Sterling, Paul Messina, and Paul Smith, okay, on enabling technologies for petaflops computing. Petaflops is just a gleam in people's eyes in 1995. We could hardly imagine how you could build a machine. Okay, in 1995, the top system in the world, okay, the number 1 on the top 500 list, had 140 processors, 170 gigaflops, the numerical wind tunnel in Japan. Number 2 machine was an Intel Paragon at Sandia National Lab with 3,680 processors. Okay. So the challenges to getting to a petaflop seemed really large. Okay. Yet, when the petascale machines arrived, they seemed like a natural next step from what people were doing in the past. And so what I and others in the community have already started to work on is the vision and the roadmap for exaflops machines, machines that have 1,000 times the capability of petaflops machines. We're driving that from what are the science and engineering needs that would give us reason to accelerate, if possible, the building of such machines. Okay, and so it started out with reports like this one, okay, on modeling and simulation at the exascale. What are the scientific drivers? So the next summit is 10 to the 18th operations a second. Machines like that will probably have 10 to 100 million cores. Okay, and we think it should be feasible by about 2022, and if we wanted to and we worked hard at it, we might be able to do it as soon as 2017, 2018. Okay, so think about that, and think about the kind of problems that might be able to be addressed that way. And thank you very much for your attention.